By minimizing the total Helmholtz energy with respect to V alpha, we found that in order for the system to be at equilibrium, one of the requirements is that both the alpha and the beta phases need to have the same pressure. Let's now go through the same analysis by minimizing the total Helmholtz energy with respect to N alpha, the number of molecules in the alpha phase. And so, if we minimize A by N alpha, so that this partial derivative is equal to 0, we then need to write out the partial derivatives for each of the A's for the alpha and beta phases. Once again, for the Helmholtz beta, we want to write it in terms of, that should be alpha. Write it not in terms of N alpha, but we want to write it in terms of N beta. So we'll do that expansion rule again. All right, and once again, we have the partial derivative of N beta over N alpha. If N beta increases, N alpha decreases. And so that means, just like what we saw with volume, that this partial derivative is going to be equal to -1. Okay? And so we have positive term here, negative term here. The sum of them is equal to 0. And so that tells us dA alpha, dN alpha, constant V alpha, and constant volume, that's equal to dA beta over dN beta at constant volume. Okay? All right, and so, we have this relationship between the two partial derivatives of the alpha and the beta phases. But we want to, kind of dig deeper into what exactly this means. All right? And so, in contrast to what we did before, in order to get more insight into what this relationship means, what we're going to do instead is look more into the Helmholtz equation. And so what we know is that our Helmholtz energy, A, we could rewrite that in terms of the molar Helmholtz energy, which would be N A squiggly. And this A squiggly would be a function of the molar volume and the temperature. All right? So what I want to highlight here is that regular A is an extensive variable, while squiggly A is an intensive variable. Okay. And this molar volume that we have here, we could also just rewrite that as total volume divided by N, and T here. All right? And so remember, we were dealing with a constant NVT system here. All right? And so this is our Helmholtz equation. And so if we take the partial derivative of A extensive with respect to N, so N total, at constant volume, what we need to do is we need to apply the chain rule, right? And so what we do is we first take the derivative of N and then multiply by A squiggly. And the derivative of N with respect to N is just A squiggly. Then we take the derivative of A squiggly and multiply it by N. Okay. At constant V. All right. But we know that A squiggly is a function of N itself, right? V over N. And so when we write it out, we also have to write out, we could rewrite the derivative like this. Okay? Where the step I took here is essentially, I did the expansion rule such that rewrote dA dN as dA over dV times dV over dN, right? And so here, I just wrote out V squiggly. But in this partial derivative, I expanded out the V over N, okay? And so the use in doing that, so if I rewrite dA dN constant V, it's going to be A squiggly minus N dA dV. And I'll write that this is at constant N, constant T, or actually, just constant T. And if we take the derivative of this with respect to N, the V is constant, you could pull that out, right? And the derivative of 1 over N with respect to N is negative 1 over N squared, okay? So we have this. And once again, we have dA dV at constant T. And we know from earlier that this is just equal to negative pressure. Okay? Should be a positive sign here. All right, and so when we simplify this equation out, what we get is that we have N, or minus NP V over N squared. One of these N's cancels. And then what we're left with is a V over N, which we know is just molar volume again. What we could then do is we could expand out our molar Helmholtz into the molar internal energy minus T S. PV here. All right. And we know that U minus PV okay, oh, whoops, I made a sign error here. Okay, so just to keep everyone on the same page, the negative sign from this cancels out with the negative sign from that. Ah, that makes more sense. Okay, in any case, so what we now know is we have U PV, and U plus PV is enthalpy. Okay, so what we have is now H squiggly minus TS, and that gives us the molar Gibbs energy. Okay, and so based on this little proof here, what we get is that if we take the derivative of the Helmholtz energy with respect to N at a constant V, that would be equal to the molar Gibbs energy, right? Even though we started with an extensive variable, in the end, we get the intensive variable here. And so the reason I went through that proof is because back up here, we have dA, dNs at constant V. And so what that tells us is that these things, for the A alpha phase and the beta phase, the derivatives of these Helmholtz with respect to N at constant V correspond to the molar Gibbs energy. So, based on this little proof, what we see is that at equilibrium, when we're minimizing the Helmholtz energy with respect to N alpha, we find that for the two phases, the molar Gibbs energy of the two phases are going to be equal. Okay? And so this is in addition to the criterion we got when we minimized Helmholtz with respect to volume. So not only do the two phases have to have the same pressure, but they also have to have the same molar Gibbs energy.